So I want to talk in a little bit more generality about some of the geometry that's going on so that we can motivate setting up some of our tangent vector with respect to u and tangent vector with respect to v. So let's think about this generally. In general, I'm taking inputs that have coordinates in my uv space. So let's say that my input is u naught, v naught. That's what this point is. But I can think of this as being a grid of a whole bunch of u values and a whole bunch of v values, just like our normal Cartesian grid. And this function, this parameterization function, is taking this grid of u's and v's and it's translating it into being some surface in three-dimensional space. So under this map, I go from being just a flat, normal-looking carpet to being what I consistently call something like a magic carpet, where each of these grid lines are now translated to be these curvy, wavy lines, right? Because my surface is some curvy, wavy surface up here in three-dimensional space. So my point down here, I'll go ahead and highlight it in green color, u naught, v naught, gets mapped over here to being at some other coordinate. Because as an input, it'll have an output now that's x of u naught, v naught, y of u naught, v naught, and z of u naught, v naught. And the things that I want to introduce that are helpful for us are the ideas of our unit tangents. So let's say that I were to consider the partial derivative just with respect to u, holding my v's exactly constant. So if my v's are held constant, it means I'm moving along this line, and I have some vector t sub u. And if I think of that t sub u over in this space, it's going to be exactly tangent to this curve where I'm holding my v's constant and my u's are allowed to change. Similarly, if I think of a vector where I hold my u's constant and my v's are allowed to change, that's going to give me some green arrow. And right at that point, maybe I should label these. My green arrow is where I held my u naughts constant and my v's are allowed to change. So we're going to call that t sub v. And we're calling our blue one t sub u. Algebraically, how are these two guys defined? Well, really, it's just the partial derivative of our function with respect to u. Maybe this looks messy, but it's not really that messy. So I'm just taking the derivative and holding v constant and seeing how does u change. Similarly, if I were to hold u constant and see how my v's changed, I would get the partial derivative of my parameterization with respect to v. Why is this helpful? I'll tell you why this is helpful. The final big conclusion is the fact that if I have some crazy crisscrossy surface up here, it's really helpful to be able to find a normal vector. That's one of the skills that we've found before that we think is helpful. And it turns out that taking the cross product of my partial derivative with respect to u and my partial derivative with respect to v will always result in a normal vector. And in this case, a normal vector would be sort of sticking straight out of the board. So it's hard for me to, visualize what this normal vector is doing, coming straight out. But we have that tu crossed with tv is going to be n, our normal vector. At that point in the space, we can evaluate it at u naught, v naught, and then we'll get the normal vector that comes out right there at u naught, v naught. So let's look at an example of computing these tangent vectors and our normal vector. Let's say that we're given a parameterization of a cylinder that's given by phi of uv is equal to 2 cosine u, 2 sine u, v. So this is giving us a cylinder that looks something like this. And the 2 is going to be a coefficient out front in our x and our y's, so it means that it has a radius 2. And really, our v can extend on infinitely in either direction, so maybe I shouldn't truncate this sphere, or this cylinder. But we get the idea that it's a cylinder that looks like this, that has radius 2. So in this case, our u is representing the angle that we're tracing out. So our different u values are going to give us different angles along this sphere. And I'll draw my u values in blue to indicate that they're going to be these vertical lines going around in a circle. Whereas our v values are corresponding exactly with our height values. So if I were to put the grid lines onto this, our v values look something like this. So if I wanted to compute what is t sub u, that's asking at some fixed point here, what is the slope of my tangent line when I hold my, I'm holding my v constant, so it means I'm holding my height constant, and I want to know what is the angle of this vector going this direction. Whereas my t sub v, I'm holding my v constant, or I'm holding my u constant now, and I'm saying what's my rate of change in my v direction. So holding a u constant means I'm looking at this vector right here. Regardless, it's pretty straightforward to compute this algebraically. Recall that this is just going to be the partial derivative of our parameterization with respect to u, which we can take partial derivatives. We know that the derivative of cosine is equal to negative sine, so I get negative 2 sine of u. The derivative of sine is cosine, so I get 2 cosine u. And the derivative of v with respect to u is just going to be 0. Similarly, when I look at my partial derivative of my parameterization with respect to v, I see that there are no v's in that component, there are no v's in that component, and the only v I get here is 1. Let's look at what the geometry of that is saying. That's saying that no matter what, our rate of change in the v direction is always 1, which makes sense that this vector is just always going to be going straight up, because this is the vector that's just going straight up of unit 1. Because as I go up this cylinder, it's not like tilting outward or tilting inward or going crazy directions, it's just going straight up. Whereas this is telling us that if we hold our radius or our height constant and we travel around in the circle, we see that our tangent vector is going to change values around in a circle, but the height is always 0, because it's not going up or down or bending at all as I travel of equal height along one of those grid lines. Our final step, let's go ahead and compute what our normal vector is going to be. Our normal vector, recall, I'll write down our definition, it's going to be the cross product of tu and tv. And we remember how to do cross products. It's going to be, our first vector is negative sine of u, positive 2 cosine of u, 0, and then 0, 0, 1. And if I look at this, I get I times 2 cosine u times 1 minus 0. So this is the vector 2 cosine u. I get j times negative 2 sine u. So I get negative 2 sine u. I know I'm not really on the board. And then I get k times 0, which is 0. So what is this telling us? This is telling us that our normal vector has no height component, and it's pointing straight out of the board, given by 2 cosine u, negative 2 sine u. And that's what my black normal vector is going to point. That's straight perpendicularly out at us from that cone, or from that cylinder.